This playlist deals with some aspects of Eurocode 2 version 2023. Watch this channel or playlist for further selected topics. This video deals with clause 8, ultimate limit state, and it's the third video on shear. You have to follow 3 basic steps when you are dealing with shear reinforcement or shear. And you need shear reinforcement when the applied shear force, tau ED, is bigger than the shear force capacity of the concrete alone. And you have to put shear reinforcement in such a way that the resistant shear or the design value of the resistant shear must be bigger than the applied design value of the shear force stress. In clause 8.2.3, it starts with a figure like it is stated here, figure 8.9, and it is immediately striking in this figure that all shear reinforcement is vertical. So you got the impression that inclined reinforcement is not allowed yet. But this is on page 121. But further on, on page 125, which is in clause 13, the inclined reinforcement is dealt with. So it's quite confusing when you are reading the code that you start with the verticals, and then later on you will find 5 or 6 pages later on, you will find that inclined reinforcement is of course allowed. So this was a little bit confusing in the beginning. The principle of shear reinforcement and shear reinforcement, the way of dealing with the shear reinforcement or calculating is the same as it was previously in Eurocode version 2004. The difference is in a name. In version of 2004, we talked about struts, compression struts. Now in 2023, we talk about compression fields instead of struts. So the basic principles are: you have a compression cord on top, a tension cord on the bottom, and they are connected with compression fields or compression struts. And then you have the definition of the angle theta and the definition of Z, the lever arm, which is from the center of the compression cord to the center of the tension cord, and which can be taken at 0.9 times the effective depth of the section. In regions where there is no discontinuity of VED, which is the shear force, for instance, for uniformly distributed loading pushing against a member, the shear reinforcement in any length increment equal to Z cotangent theta may be calculated using the smallest value of the shear force in the increment. Then between brackets, except in members under high water or gas pressure. What do they mean by high? How much is high? So at least it should be clarified what high water and gas pressures, what is the value, what is low and what is high. And when you have high water or gas pressure, how do you deal with it? It only says that you can use this method, taking the lowest value in increment L equals Z cotangent theta. But what do you do when there is a high water or gas pressure? In the videos on beams, I used the same clause, but instead of Z cotangent theta, I used D cotangent theta. And in fact, this is not like it was meant in the code. This was used many years ago, in the years 1980, 1985, then it was used D cotangent theta. But in the Eurocode, it is clearly stated Z cotangent theta. Now, why did we use D cotangent theta? Because there was a distinction made between the location of the cracks and the lever arm that is used in the calculations of VRDS, which is the resistant shear force with shear reinforcement. Just to explain you a little bit, if you have the compression cord and the tension cord, Z is defined by this value here, and D is the effective depth of the beam. Now, Z is equal to 0.9 D. I made the assumption, or I believe that cracks the ends at the top of the beam. So when it ends at the top, it starts at the tension cord, at the reinforcement, and it ends at the top of the beam. That's why I use D. Here, I don't use H, the total depth, because this is in tension. So concrete that is in tension, we do not count. This is a compression. So concrete that's in compression, we take into account. So because the crack ends on the top, I used D cotangent theta, this value. Now, what is the error that you make? What is the error if you do not follow the Z cotangent theta, but you use the D cotangent theta? Well, the difference is simple. For cotangent theta between 1 and 2.5, the ratio theta calculated with Z or theta calculated with D, you will see it's 0.9 or 0.93. So it's only, in fact, the inclination of the compression strut. If you choose it a little bit different, you can use D cotangent theta or Z cotangent theta. So the difference is not huge. But you should use in the code 2023 Z cotangent theta. That is now clearly stated in the clause 8.2.3 part. The inclination of the compression field, the cotangent theta of this inclination should be between 1 and cotangent theta min, the minimum value. Just remember that compression field in Eurocode 2023 is the same as compression struts in Eurocode 2004. For shear force, for shear reinforcement ductility class B and C, cotangent theta min is defined in those formulas here. For no actual force, the most common cases, no actual force, cotangent theta min is 2.5 with sigma CP equals 0. So the normal forces, tension or compression, is not there. Then we have cotangent theta min is 2.5. When you have significant actual compressive forces, that means when the sigma CP is between 0 and 3 megapascal, and X is smaller than 1.5 times D, then cotangent theta min is given by this formula. Which is striking is why do they put the absolute value? It is for actual compressive forces. So a compressive force is normally a negative sign, so you should put here 2.5 minus sigma CP divided by 6. That's clear. But now they have said it's plus, and then the absolute value of sigma CP, because sigma CP is the compressive force. Okay, it's a little bit confusing. And cotangent theta min is equal to 3, not 2.5, when you have a very significant compressive force, bigger than 3 megapascal. For actual tension, then cotangles theta min. You should subtract a certain value of it, but not, but it should always be larger, of course, than 1. For a ductility class A, cotangles theta min is 0.8 times the cotangles theta min for the ductility class B and C. So you have to use these formulas and multiply it by 0.8. So it's a little bit more complicated than we used to in the Eurocode version 2004. The shear stress resistance at yielding of the shear reinforcement is given by formula 8.42. So tau RD X equals the reinforcement ratio, or the multiplied by the stress, the yielding stress of the reinforcement, and multiplied by the cotangles of the theta. Just remember that the shear stress is defined as the shear force divided by BW.9D. The rho W is equal to the cross section of the shear reinforcement divided by the width B and divided by the spacing of the shear reinforcement. You must also apply to formula 8.44, which is the maximum stress in the compression field or in the struts, and that stress must be smaller than nu FCD, and the stress is calculated as the applied shear stress multiplied by cotangles theta plus tangles theta. You can reformulate formula 8.44 in the way like it is shown in this formula. So this is not in the code. It's something that I prefer to use, because you need to know what is theta. Theta is unknown in the start of your calculation. So you can use a theta, for instance, the smallest one. And then you do your calculation, you check it with 8.4, and you find that, and then you can find out that the stress in the compression field is too large. Then you have to redo your calculations with an adapted theta. Or you can make it easy. You can rewrite this formula in such a way that from this formula, you can directly calculate the minimum theta that you need to fulfill the stress in the compression field. So it's just an easier way to calculate it. Nu is equals to 0.5. And in 8.2.37, it is stated that can be calculated. Nu can be calculated with different formulas that is stated in the clause that I just mentioned. But this is for theta smaller than theta. So this I do not understand. Why is theta min defined? And later on, they say that you can have a theta which is smaller than theta min. So now what is it now? Is it allowed? Is it not allowed? And they say if this is the case, if theta is smaller than theta min, you should adapt the coefficient nu. So it means that you must restrict the compression in the compression field stress. So it's a little bit strange, yes. You can now, because everything is formulated in stresses. So that's very consistent. That's true, but in practice, it's more difficult to apply. So you can now use this formula 8.4, you can rework it, and you can make it in this way that you can calculate directly the maximum shear force that is allowed in a section to fulfill the compression field requirements. So it's the same formula as this, and you have now this easy applicable formula to calculate the VRD max. So in function of theta, you will have different maximum values of the shear force, allowable shear force. We can make a graph. On the x-axis. It's the concrete quality, and on the y-axis it's the VRD max. It's the maximum allowable shear force due to the contraction field. For each for each theta or cotangent theta, you can make a graph like that. So we've used now here cotangent theta equals 2.5, and the red curve is the one calculated with the present code of 2004, and the blue one of the code of 2023. You see that it's almost the same, but there is a difference. And when we enlarge the difference, and we take on the y-axis the maximum shear force of calculated through the version of 2023 divided by the value calculated through the version of 2004, then you will see that in all concrete classes, the maximum allowable shear force due to the compression field is smaller in the present code, but that difference is not very high, and this difference is only due to the other definitions of FCD. And remember, FCD, there's now a term theta C in it, and the definition of nu, of course. So the difference is not very large. It's only a 3% decrease for values larger than 30 megapascal. It's a mean value of 3%, something like that in this region. So the influence is not very big.